Here I've done two things at the same time. I've both interpreted the universal quantification of x and also interpreted the OR. And that has to be the case whichever value I pick for my x. So whichever element from my domain I pick, if I modify my substitution that way, then either phi of x has to be true in that modified substitution, or psi of x has to be true. Yeah? Still with me? One step further, I can say that if that is the case, then what? Yes. Okay. What this says is, if there is a value for x such that psi x evaluates to true, then I can reformulate that fact to saying the formula that exists in x such that psi of x is evaluates to true in the original sigma. How? I have to say that again because that didn't come out very well. If I can find a value for x such that psi x is true, that's exactly the same as saying that the formula exists x such that psi x is true under the unmodified substitution. This might be easier to understand when read from right to left, because that's in fact exactly the definition of evaluating an existentially quantified formula. If I want to evaluate this existentially quantified formula under sigma, what I have to do is to find a value for x such that the modified substitution makes psi of x true. Yeah, so this is essentially a definition of the semantics of the existential quantification. If there is not a value for x that makes psi of x true, then from the second line I may conclude that it must be the case that phi of x is true for all possible values. Yeah, because this said that for all values either phi of x or psi of x is true. If psi of x is never true, then phi of x must be always true. And that in turn can be re-encoded as a statement that for all x, phi x must be true in under sigma. Well, and that together gives me the desired conclusion, because either in case 3 or in case 4, this disjunction evaluates to true. Okay, long story, and this might be hard to understand because it is so trivial in a sense. Because what I'm doing, essentially, I'm taking the formula over here, which I hope you all have an intuitive understanding of, and I'm completely formalizing that intuitive understanding. But if your intuition is already good enough, then this formalization just copies what you intuitively know, and then it might be difficult to see what's going on. Yeah, but what is going on is really trying to really completely formally define all the steps that you intuitively follow in order to understand that this is a formula, the valid formula. Enough about that. So now we essentially have learned the notion of the semantics of a predicate formula. And now we go through the concepts again that we've covered for proposition logic in order to establish either semantically or syntactically that formulas are actually valid or satisfiable or unsatisfiable. To start with semantic tableaus. This is what we already knew. This is what you have yourself applied in doing the homework exercises. We had these tables which tell you how to split up a node in a semantic tableau, either actually branching or non-branching, depending on the top-level operator in in a formula in that node. So this is just a copy of an earlier slide, but we are now in an extended world. We are in the world of predicate logic. So we have to also find a way to deal with contours. So let's take the formula over here. The formula is saying not for all x, px implies qx implies for all x, px implies for all x, qx. So what does this say? You can read it like this says that universal quantification does not distribute over implication. Well, what do you expect? Is this formula itself satisfiable, unsatisfiable, valid, contradictory? What is your expectation here? Maybe it's easier if I ask the question without the outer negation. I think I missed the bracket here. What do you think about this formula? Is this valid, satisfiable, unsatisfiable? What do you think? In other words, does universal quantification distribute over implication? Who votes for valid? I want some movement here. I see several, 3, 4 votes for valid. Who thinks it's invalid? Nobody thinks it's invalid. Who thinks it's at least maybe not valid, but at least satisfiable? Yeah, everybody who thinks it's valid should now also raise their hands because they should also think it's satisfiable. Yeah. So we are now. We have the majority of votes who at least think it's satisfiable, which means there is an interpretation in which this holds. And that would mean that an attempt to show it to be unsatisfiable must fail. Yeah? So I'm going to try and show it unsatisfiable. That's wrong. I'm going to try and show that the negation is unsatisfiable. I'm going to try and show that the formula itself is valid by showing that its negation is unsatisfiable. Okay, let's do that. What is the first step? So I'm going to use the method of semantic tableau. What is my first step?
Negation.
Sorry?
Negate it?
I already negated it, so that's...
Let's see it. Right.
No, it's I have a different pen which is more black than the previous. Now you can see it. Okay, what do I do first?
We have to get rid of the negation and implication.
Yes.
To split it.
Well, in fact, this is not even a splitting rule, I believe. Is it? No, it's not.
Oh, yeah, but
you get two formulas. I think what you get is for all x, px implies qx as your first formula, and the other formula would be not for all x, px implies for all x, qx. Yeah, this is the rule that you already knew from propositional logic. In fact, nothing new here. What next?
Remove the negation on the second formula?
Yes, same story. I still have a formula with implication as its top level operator, or actually negation as its top level operator, then implication. So same story, and out comes for all x, px implies qx, and then for all x, px, and not for all x, qx. Now what? Now the rules I had no longer tell me what to do. Because all my formulas have either universal quantification as their top level operator or negated universal quantification. The idea now is that that I can say, well, suppose that I have a non-empty domain. The fact that for all x px means that there is some individual for which px holds. Or I can also look at this formula and say the fact that not for all x qx must mean that there is at least one individual for which qx does not hold. Now let's just name that individual. I'm going to introduce a constant that wasn't in my vocabulary before, which I imagine to stand for that value for which qx doesn't hold. So, in my next step, I introduce a new constant, a fresh constant, and I say, okay, that is the one for which qx doesn't hold. So that's, I'm going to name it A, it's just a fresh constant. And I'm saying that's the one for which qa doesn't hold. This is one way to get rid of either an existentially quantified formula in your semantic tableau or a negated universally quantified formula. Just saying, okay, they both state something about the existence of a value. Let's just name that value. Okay. The other formulas stay as they are for the moment.